IP compression. 2. Adding a zero stage to the HP compression. 3. Improving the compression process, without adding stages, for example higher fan hub pressure ratio. All of which increase both overall pressure ratio and core airflow. Alternatively, the core size can be increased, to raise core airflow, without changing overall pressure ratio. This route is expensive, since a new, upflowed, turbine system, and possibly a larger IP compressor, is also required. Changes must also be made to the fan to absorb the extra core power. On a civil engine, jet noise considerations mean that any significant increase in takeoff thrust must be accompanied by a corresponding increase in fan mass flow, to maintain a T/O specific thrust of about 30 lbf/pound/s. Technical discussion, edit. 1. Specific thrust, net thrust /intake airflow, is an important parameter for turbofans and jet engines in general. Imagine a fan, driven by an appropriately sized electric motor, operating within a pipe, which is connected to a propelling nozzle. It is fairly obvious, the higher the fan pressure ratio, fan discharge pressure /fan inlet pressure, the higher the jet velocity and the corresponding specific thrust. Now imagine we replace this setup with an equivalent turbofan, same airflow and same fan pressure ratio. Obviously, the core of the turbofan must produce sufficient power to drive the fan via the low pressure, LP, turbine. If we choose a low, HP, turbine inlet temperature for the gas generator, the core airflow needs to be relatively high to compensate. The corresponding bypass ratio is therefore relatively low. If we raise the turbine inlet temperature, the core airflow can be smaller, thus increasing bypass ratio. Raising turbine inlet temperature tends to increase thermal efficiency and, therefore, improve fuel efficiency. 2. Naturally, as altitude increases, there is a decrease in air density and, therefore, the net thrust of an engine. There is also a flight speed effect, termed thrust lapse rate. Consider the approximate equation for net thrust again. F sub n equals m times open paren v sub jf of e minus v sub a close paren period. With a high specific thrust, for example, fighter, engine, the jet velocity is relatively high, so intuitively one can see that increases in flight velocity have less of an impact upon net thrust than a medium specific thrust, for example, trainer, engine, where the jet velocity is lower. The impact of thrust lapse rate upon a low specific thrust, for example, civil, engine is even more severe. At high flight speeds, high specific thrust engines can pick up net thrust through the ram rise in the intake, but this effect tends to diminish at supersonic speeds because of shock wave losses. 3. Thrust growth on civil turbofans is usually obtained by increasing fan airflow, thus preventing the jet noise becoming too high. However, the larger fan airflow requires more power from the core. This can be achieved by raising the overall pressure ratio, combustor inlet pressure /intake delivery pressure, to induce more airflow into the core and by increasing turbine inlet temperature. Together, these parameters tend to increase core thermal efficiency and improve fuel efficiency. For some high bypass ratio civil turbofans use an extremely low area ratio, less than 1.01, convergent-divergent, nozzle on the bypass, or mixed exhaust stream, to control the fan working line. The nozzle acts as if it has variable geometry. At low flight speeds the nozzle is uncoked, less than a Mach number of unity, so the exhaust gas speeds up as it approaches the throat and then slows down slightly as it reaches the divergent section. Consequently, the nozzle exit area controls the fan match and, being larger than the throat, pulls the fan working line slightly away from surge. At higher flight speeds, the ram rise in the intake increases nozzle pressure ratio to the point where the throat becomes choked, m equals 1.0. Under these circumstances, the throat area dictates the fan match and, being smaller than the exit, pushes the fan working line slightly towards surge. This is not a problem, since fan surge margin is much better at high flight speeds. 5. The off-design behavior of turbofans is illustrated under compressor map and turbine map. 6. Because modern civil turbofans operate at low specific thrust, they require only a single fan stage to develop the required fan pressure ratio. The desired overall pressure ratio for the engine cycle is usually achieved by multiple axial stages on the core compression. Rolls-Royce tend to split the core compression into two with an intermediate pressure, IP, supercharging the HP compressor, both units being driven by turbines with a single stage, mounted on separate shafts. Consequently, the HP compressor need develop only a modest pressure ratio, for example, ~4.51. US civil engines use much higher HP compressor pressure ratios, for example, ~23.1 on the General Electric GE90, and tend to be driven by a two-stage HP turbine. Even so, there are usually a few IP axial stages mounted on the LP shaft, behind the fan, to further supercharge the core compression system. Civil engines have multi-stage LP turbines, the number of stages being determined by the bypass ratio, the amount of IP compression on the LP shaft and the LP turbine blade speed. 7. Because military engines usually have to be able to fly very fast at sea level, the limit on HP compressor delivery temperature is reached at a fairly modest design overall pressure ratio, compared with that of a civil engine. Also, the fan pressure ratio is relatively high, to achieve a medium to high specific thrust. Consequently, modern military turbofans usually have only 5 or 6 HP compressor stages and require only a single stage HP turbine. Low bypass ratio military turbofans usually have one LP turbine stage, but higher bypass ratio engines need 2 stages. In theory, by adding IP compressor stages, a modern military turbofan HP compressor could be used in a civil turbofan derivative, but the core would tend to be too small for high thrust applications. Improvements, edit. Aerodynamic modeling, edit. Aerodynamics is a mix of subsonic, transonic and supersonic airflow on a single fan /gas compressor blade in a modern turbofan. The airflow past the blades has to be maintained within close angular limits to keep the air flowing against an increasing pressure. Otherwise the air will come back out of the intake. The full authority digital engine control, FADEC, needs accurate data for controlling the engine. The critical turbine inlet temperature, TIT, is too harsh an environment, at 1700 degrees Celsius. 3100 degrees Fahrenheit, and 17 bar, 250 psi, for reliable sensors. Therefore, during development of a new engine type a relation is established between a more easily measured temperature like exhaust gas temperature and the TIT. Monitoring the exhaust gas temperature is then used to make sure the engine does not run too hot. Blade technology, edit. A 100G, 3.5 ounces, turbine blade is subjected to 1700 degrees Celsius, 3100 degrees Fahrenheit, at 17 bar, 250 psi, and a centrifugal force of 40 kN, 9000 lbf, well above the point of plastic deformation and even above the melting point. Exotic alloys, sophisticated air cooling schemes and special mechanical design are needed to keep the physical stresses within the strength of the material. Rotating seals must withstand harsh conditions for 10 years, 20,000 missions and rotating at 10 to 20,000 RPM. Fan blades, edit. Fan blades have been growing as jet engines have been getting bigger. Each fan blade carries the equivalent of 9 double-decker buses and swallows air the equivalent volume of a squash court every second. Advances in computational fluid dynamics, CFD, modeling have permitted complex, 3D curved shapes with very wide chord, keeping the fan capabilities while minimizing the blade count to lower costs. Coincidentally, the bypass ratio grew to achieve higher propulsive efficiency and the fan diameter increased. Rolls-Royce pioneered the hollow, titanium wide-chord fan blade in the 1980s for aerodynamic efficiency and foreign object damage resistance in the RB211, then for the Trent. GE Aviation introduced carbon fiber composite fan blades on the GE90 in 1995. Manufactured today with a carbon fiber tape layer process. GE partner Safran developed a 3D woven technology with Albany composites for the CFM56 and CFM LEAP engines. Future progress, edit. Engine cores are shrinking as they are operating at higher pressure ratios and becoming more efficient, and become smaller compared to the fan as bypass ratios increase. Blade tip clearances are harder to maintain at the exit of the high-pressure compressor where blades are 0.5 in, 13 mm, high or less. Backbone bending further affects clearance control as the core is proportionately longer and thinner and the fan to low-pressure turbine drive shaft is in constrained space within the core. Pratt & Whitney VP Technology and Environment Alan Epstein argued over the history of commercial aviation. We have gone from 20% to 40% cruise efficiency, and there is a consensus among the engine community that we can probably get to 60%. Geared turbofans and further fan pressure ratio reductions may continue to improve propulsive efficiency. The second phase of the FAA's Continuous Lower Energy, Emissions and Noise, Clean program is targeting for the late 2020s reductions of 33% fuel burn, 60% emissions and 32 dB EPNDB noise compared with the 2000s state-of-the-art. In summer 2017 at NASA Glenn Research Center in Cleveland, Ohio, Pratt has finished testing a very low pressure ratio fan on a PW1000G, resembling an open rotor with fewer blades than the PW1000G S20. The weight and size of the nacelle would be reduced by a short duct inlet, imposing higher aerodynamic turning loads on the blades and leaving less space for soundproofing, but a lower pressure ratio fan is slower. UTC Aerospace Systems Aerostructures will have a full-scale ground test in 2019 of its low-drag integrated propulsion system with a thrust reverser, improving fuel burn by 1% and with 2.5-3 and lower noise. Safran expects to deliver another 10-15% in fuel efficiency through the mid-2020s before reaching an asymptote, and next will have to introduce a breakthrough to increase the bypass ratio to 35:1 instead of 11:1 for the CFM LEAP. It is demonstrating a counter-rotating open rotor unducted fan, Turbofan, in Istres, France, under the European Clean Sky Technology Program. Modeling advances and high specific strength materials may help it succeed where previous attempts failed. When noise levels will be within current standards and similar to the LEAP engine, 15% lower fuel burn will be available, and for that Safran is testing its controls, vibration and operation, while airframe integration is still challenging. For GE Aviation, the energy density of jet fuel still maximizes the Breguet range equation, and higher pressure ratio cores, lower pressure ratio fans, low loss inlets and lighter structures can further improve thermal, transfer and propulsive efficiency. Under the U.S. Air Force's Adaptive Engine Transition Program, Adaptive thermodynamic cycles will be used for the 6th generation jet fighter, based on a modified Brayton cycle and constant volume combustion. Additive manufacturing in the advanced turboprop will reduce weight by 5% and fuel burn by 20%. Rotating and static ceramic matrix composite, CMC, parts operates 500 degrees Fahrenheit, 260 degrees Celsius, hotter than metal and are 1/3 its weight. With $21.9 million from the Air Force Research Laboratory, GE is investing $200 million in a CMC facility in Huntsville, Alabama, in addition to its Asheville, North Carolina site, mass-producing silicon carbide matrix with silicon carbide fibers in 2018. CMCs will be used 10 times more by the mid-2020s. The CFM LEAP requires 18 CMC turbine shrouds per engine and the GE9X will use it in the combustor and for 42 HP turbine nozzles. Rolls-Royce plc aim for a 61 pressure ratio core for the 2020 Ultrafan and began ground tests of its 100,000 HP, 75,000 kilowatts, gear for 100,000 lbf, 440 kN, and 15:1 bypass ratios. Nearly stoichiometric turbine entry temperature approaches the theoretical limit and its impact on emissions has to be balanced with environmental performance goals. Open rotors, lower pressure ratio fans and potentially distributed propulsion offer more room for better propulsive efficiency. Exotic cycles, heat exchangers and pressure gain / constant volume combustion may improve thermodynamic efficiency. Additive manufacturing could be an enabler for intercooler and recuperators. Closer airframe integration and hybrid or electric aircraft can be combined with gas turbines. Current Rolls-Royce engines have a 70–82% propulsive efficiency and 40–49% thermal efficiency for a 0.63 0.49 pound/lbf/h. 64,00050,000 G/kn/h, TSFC at Mach 0.8, and aim for theoretical limits of 95% for open rotor propulsive efficiency and 60% for thermal efficiency with stoichiometric turbine entry temperature and 81 overall pressure ratio for a 0.35 pound/lbf/h. 36,000 G/kn/h, TSFC. As teething troubles may not show up until several thousand hours, the latest Turbofan's technical problems disrupt airlines' operations and manufacturers' deliveries while production rates rise sharply. Trent 1000 cracked blades grounded almost 50 Boeing 787s and reduced tops to 2.3 hours down from 5.5, costing Rolls-Royce plc almost $950 million. PW1000G knife edge seal fractures have caused Pratt & Whitney to fall behind in deliveries, leaving about 100 engineless A320neos waiting for their power plants. The CFM LEAP introduction had been smoother, but a ceramic composite HP turbine coating was prematurely lost, necessitating a new design, causing 60 A320neo engine removals for modification and delaying deliveries by up to 6 weeks late. On a widebody, Safran estimates 5–10% of fuel could be saved by reducing power intake for hydraulic systems, while swapping to electrical power could save 30% of weight, as initiated on the Boeing 787, while Rolls-Royce plc hopes for up to 5%. Manufacturers, edit. Main article, list of turbofan manufacturers. The turbofan engine market is dominated by General Electric, Rolls-Royce plc and Pratt & Whitney, in order of market share. General Electric and Safran of France have a joint venture, CFM International. Pratt & Whitney also have a joint venture, International Aero Engines, with Japanese Aero Engine Corporation and MTU Aero Engines of Germany, specializing in engines for the Airbus A320 family. Pratt & Whitney and General Electric have a joint venture, Engine Alliance, selling a range of engines for aircraft such as the Airbus A380. For airliners and cargo aircraft, the in-service fleet in 2016 is 60,000 engines and should grow to 103,000 in 2035, with 86,500 deliveries according to Flight Global. A majority will be medium thrust engines for narrow-body aircraft, with 54,000 deliveries, for a fleet growing from 28,500 to 61,000. High-thrust engines for wide-body aircraft, worth 40–45% of the market by value, will grow from 12,700 engines to over 21,000, with 18,500 deliveries. The regional jet engines below £20,000, 89 kN, fleet will grow from 7,500 to 9,000, and the fleet of turboprops for airliners will increase from 9,400 to 10,200. The manufacturer's market share should be led by CFM with 44%, followed by Pratt & Whitney with 29%, and then Rolls-Royce and General Electric with 10% each. Commercial turbofans in production, edit. Commercial turbofans in production. Model start bypass length fan weight thrust major applications. GEGE 1992 8.79.95.18 5.40 M3.12 3.25 M7.56 8.62 T335 10 KNB 777 P&W PW 4000 1984 4.86.43.37 4.95 M2.84 M4.18 7.48 T2222436 KN a 300/310, a 330, B747, B767, B777, MD11. R Trent XWB 2010 9.35.22 M3.00 M7.28 T33430 KN a 350 XWB. R Trent 800 1993 5.75.79 4.37 M2.79 M5.96 5.98 T411.425 KNB 777. EAGP 7000 2004 8.74.75 M2.95 M6.096.71 T311363 KN a 380. R Trent 900 2004 8.74.55 M2.95 M6.18 6.25 T34357 KN a 380. R Trent 1000 2006 10.811 4.74 M2.85 M5.77 T265.3360.4 KNB 787. GEGX 2006 8.09.34.31-4.69 M2.66-2.82 M5.62-5.82 T296 to 339 KNB 747-8, B787. R Trent 700 1994.93.91 M2.47 M4.79 T320 KN a 330. GECF 6 1971 4.35.34.004.41 M2.22.79 M3.82 5.08 T22228 KN a 300/310, a 330, B747, B767, MD11, DC10. R Trent 519.99 8.53.91 M2.47 M4.72 T252 KN 340-500/600. PW 1000 G2008 9.012.53.40 M1.42 2.06 M2.86 T67 160 KN 320 Neo, a 220, E-Jets E2. CFM League 2013 9.011.03.15 3.33 M1.76 1.98 M2.78 3.15 T100 146 KN 320 Neo, B737 Max, C919. CFM 56 1974 5.06.62.36 2.52 M1.52 1.84 M1.95 2.64 T97.9-151 KN a 320, a 340-200/300, B737, KC 135, DC8. IAEV 2519.87 4.44.93.20 M1.60 M2.36 2.54 T97.9-147 KN a 320, MD90. PW 6000 2000 4.902.73 M1.44 M2.36 T100.2 KN Airbus A318. RBR 719.94 4.24.53.41 3.60 M1.32 1.58 M1.63 2.11 T68.910 2.3 KNB 717, Global Express, Gulfstream V. GE Passport 2013 5.63.37 M1.30 M2.07 T78.984.2 KN Global 7000/8000. GECF 34 1982 5.36.32.62 3.26 M1.25 1.32 M0.74 1.12 T41 82.3 KN Challenger 600, CRJ, E-Jets. PW 800 2012 5.51.30 M67.469.7 KN Gulfstream G500/G600. RTA 1984 3.13.22.41 M1.12 1.14 M1.42 1.53 T61.668.5 KN Gulfstream 4, Vodka 70/100. Silvercrest 2012 5.91.90 M1.08 M1.09 T50.9 KN Citation Hemisphere, Vulcan 5X. RA 3007 1991 5.02.71 M1.11 M0.72 T33.7 KN ERJ, Citation X. PW 300 1988 3.84.51.92 2.07 M0.97 M0.45 0.47 T23.435.6 KN Citation Subrin, G200, Vulcan 7X, Vulcan 2000. HWHTF 7000 1999 4.42.29 M0.87 M0.62 T28.9 KN Challenger 300, G280, Legacy 500. HWTFE 7311972.67.3.9.52.0.78M0.74.0.45T15.622.2KN Learjet 70/75 G150 Vulcan 900 Williams FJ 44 1985 3.34.11.36 2.09 M0.53 0.57 M0.21 0.24 T6